Welcome to Algebra 1, Unit 8, Lesson 7-1, Solving Systems by Graphing. Pearson Algebra 1, copyright 2009. I'm Mr. Pilarski, and our objectives today are, I will be able to solve systems of equations by graphing, and I will be able to analyze special types of systems. As we work through our three examples today, we're going to be taking a look at how to solve systems of equations by graphing. In each example, we're going to analyze the special type of system or give the system a name. Graphing review. There's three basic ways that you've been taught how to graph in Unit 6. The first way was to find the x and the y intercepts. That is best if the x and the y are on the same side. That's also known as standard form. So if an equation is in standard form, you're going to want to use the x and y intercepts method. That's also known as the 0, 0 method. It's also known as the 0, 0 method. The second way you were taught how to graph was using the slope m and the y-intercept b, and that's usually best if the y is already solved for, if the y is by itself. Another way that works is solving for y and making a table picking x values. If you're not quite sure how to use the slope and the y-intercepts, you could also solve for y and make a table by picking x values and then finding the corresponding y values. Let's take a look at our examples today. Solve each system of equations by graphing. Here we have the equation y is equal to negative 3x plus 2 and y is equal to 3x minus 4. Well, to do this, we're going to start with the equation y is equal to negative 3x plus 2. Since this is already solved for y, we're going to identify the slope, which is m, and we're going to identify the y-intercept, which is b. Now recall that these equations are in slope-intercept form. Y is equal to mx plus b, where the m is the slope and the b is the y-intercept. So in this particular equation, y is equal to negative 3x plus 2, the slope is negative 3, and the y-intercept is 2. So what that means, or how we use this information to create a graph, we first plot the y-intercept, which is a positive 2, which means we go up 2 along the y-axis and we put our point. Then we use our slope, which is negative 3, or we could write as negative 3 over 1, which means we're going to plot additional points, we're going to go down 3 and to the right 1 from this point here. So from here, the y-intercept, we're going to go down 1, 2, 3, to the right 1, and we can repeat that pattern until we're out of room. The more points you have, the more accurate your graph or your line is going to be. Now that I have several points graphed, I can draw in a line that represents that linear equation. And there it is. So this is the equation, y is equal to negative 3x plus 2. Now we move on to y is equal to 3x minus 4. To graph this, we use the idea that it is in slope-intercept form. We identify the slope and the y-intercept. The slope of this line is equal to 3, and the y-intercept is equal to a negative 4. So first we plot the y-intercept. So from the origin, we go down 4 and plot the y-intercept right there. And then we use the slope, which is a positive 3, or 3 over 1. And from there, we'll go up 3 to the right 1, up 3 to the right 1, and we'll repeat that pattern until we run out of room. Remember, the more points you use, the more accurate your line's going to be. And we can see here that the two lines cross at this point. The two lines cross at this point right here, and that point is considered to be the solution of the linear system, or the system of linear equations. And we need to identify that point by its ordered pair. So from the origin, we have to go to the right 1 and down 1. So the ordered pair is 1, negative 1. So the solution to this system of equations is 1, negative 1. The solution to a system of equations is the point at where the two lines intersect. And when we have intersecting lines, the system has one solution, and that solution is the point where the two lines cross. And we also call that consistent and independent. Moving on to example B, if we take a look at the green equation, y is equal to 5x minus 4, it's in that slope-intercept form, so we can use the slope and the y-intercept. The slope of the green equation is 5, and the y-intercept is negative 4. So to graph that, as we saw in the previous example, we first plot the y-intercept, which in this case is a negative 4. So from the origin, we go down 4, 2, 3, 4. And from there, we use the slope to graph additional points. In this case, the slope is a positive 5, so that's up 5 to the right 1. So up 5 to the right 1. Up 5 to the right 1. And now that I have that, and I used the wrong color line there, we can adjust that color. And we draw a line through our 3 points. And we have graphed our first equation, the green equation. The second equation is in close to that standard form. Key thing to remember here is that the x and the y are on the same side, so it's pretty easy to use the 0, 0 method, or the finding the x and the y intercepts. To find the x and the y intercepts, we choose x to be equal to 0, which will help us find the y-intercept. So we substitute 0 in for x. When we substitute 0 in for x, this minus 10x goes away and leaves us with 2y is equal to negative 8. And we solve that equation for y by dividing each side by 2. And that leaves us y is equal to negative 4. So the y-intercept is negative 4. And we can see that that point falls right on the point from the other equation. Now to find the x-intercept, we choose y to be equal to 0. When y is equal to 0, the 2 times y ends up going away because 2 times y, or 2 times 0 is 0, and that will leave us with negative 10x is equal to 8. We solve this equation by, it should be negative 10x is equal to negative 8. We divide each side by negative 10, and when we simplify this, x ends up being equal to a positive 4/5, or approximately 0.8. So we need to graph that, and that 0.8, in fact, would end up being right about there. And you can see it falls right on the green line. So when I go to draw my line through these 2 points, we see that the equations fall right on top of each other, which means that they are the same line. And how we interpret that special system, we have the same lines, which means our solution is infinitely many solutions, and we also call that consistent and dependent. If the lines touch either in one place, like in example A, or if they touch in all places, like in example B, the system is considered to be consistent. Now, if it only touches or they cross at one point, that's independent, and then, as in this example, they end up being the same line, so that's called dependent. Moving on to our third example here, solve each system of equations by graphing. The first equation's in that slope-intercept form, y is equal to 3x minus 5, or plus 5. Remember, that's y is equal to mx plus b. We identify the slope. The slope is 3, and the y-intercept is 5. So as we've seen in the previous examples, first we plot the y-intercept, and in this case, that's a positive 5, so that's up 5 from the origin. and we use the slope to graph additional points, and the slope is 3, or 3 over 1, which means we're going to go up 3 into the right 1. So up 3 into the right 1, but we're out of room to put more points. So we go back to the y-intercept and we do the exact opposite of up 3 into the right 1, which would be down 3 into the left 1, and we can continue that pattern until we're out of room. Remember, the more points you can put, the more accurate your linear graph is going to be. And so there's that equation. Now, the second equation in blue is 2y minus 6x is equal to negative 2. Even though the x's and the y's are on the same side, another method for graphing this kind of equation would be to solve the equation for y and then use the slope and the y-intercept. So to solve this equation for y, we'd add 6x to both sides, which gives us 2y is equal to 6x minus 2, and then we divide both sides of that equation by 2. On the left-hand side, the 2's divide out, leaving us with the y. And on the right-hand side, when I simplify this fraction, 6x divided by 2 gives 3x, and minus 2 divided by 2 gives a minus 1. So then we can identify the slope and the y-intercept. The slope of this line is 3, and the y-intercept is a negative 1. So we plot the y-intercept, and we use the slope to plot additional points. The slope in this case is 3 over 1, so from the y-intercept I go up 3 to the right 1, and I use that pattern to continue to plot more points until I run out of room. As I did with the green equation, I can go back to the y-intercept and do the exact opposite of up 3 into the right 1, which would be down 3 to the left 1, and continue that pattern until I run out of room. And hopefully you notice that these two lines end up being parallel. They're never going to touch. And as we learned back in Unit 6, if two lines are parallel, they're going to have the same slope. And we can see that since I solved each equation for y and identified the slope, they have the same slope, but different y-intercepts, which by definition makes the lines parallel. So when we go to solve this system by graphing, these two lines are never going to cross, so there's no solution here. And that brings me to my last slide. If we have parallel lines, the solution is no solution, and we call that special situation inconsistent. This has been Mr. Pilarski on solving systems of linear equations by graphing. Thanks for watching. Bye-bye.